Okay, all right. Well, happy Wednesday. I hope you enjoyed your weekend, and it's June, so this is it. It's last couple days of the school year. Some of you are graduating, so yay. Anyway, okay. Let's talk about the final exam. We got like the best time slot for the final, right? Monday. That's what we want, right? So anyway, it's always like a bummer when your final's scheduled for Friday. It's a bummer for me also, but anyway. Okay, so we got Monday, and it's the best time slot of the day, 11:30. It's not the 8 a.m. one, and it's not like the 6 p.m. one or something. So anyway, right here, 3 hours, pen and paper. And then, as always, you can have a sheet of notes, writing or typing on the front and back, and I'll send out a seating chart. And here's the list of topics, okay? So first, you'll do a KNN classifier. I think this should be easy. I don't know. I was like, I think, I don't know. Okay. So I'm going to provide some labeled two-dimensional training data. All right, and that's basically, it's going to be an n by 2 matrix and a vector of the labels, basically. And then I'll give you a grid so you can kind of plot the data, because I think that'll make it easier if you plot the data. And then I'll provide a test case. So it'll be like, here's your new test case at 2, 3, or a new test case at -2, 0 or something. And now I'm going to ask, how would test case 1 be classified if k equals 1? Or how would it be classified if k equals 3? Or how would it be classified if k equals 5? Okay? And that's it, okay? Now, if you plot it, I mean, you don't even have to do the distance calculations. You can probably just look, just look and figure out the distances. But yeah, I mean, certainly doing the distance calculations won't hurt either. Okay, so that's the KNN classifier. I think that should be pretty straightforward in my opinion. Okay, number 2 will be support vector machines. And I will have some training data. The training data will have 2 classes. Class 1, class 2, or class plus and class minus, okay? And I'm going to run SVM several times on the exact same training case, all right? It's just every time I run it, I'm going to just modify a couple of these parameters. And I'm just going to use the computer's SVM. So I'm going to say, do SVM with cost equals 1, or SVM with cost equals 100. Do SVM with gamma equal to 0.1 or gamma 1 or gamma 5. Okay, not necessarily these exact numbers, okay? But different enough where it should be clear. I'm not going to do like gamma 0.1 and gamma 0.2, okay? It'll be different enough where it should be clear what the that there are differences, okay? And then we'll have linear versus radial kernels, okay? As radial being the Gaussian kernel, where it can be all squiggly, and linear obviously has to be a straight line type of business. And basically, I'll provide the plots that get output, and I'll also provide like the lines that I ran, okay? And it'll be kind of like, in second grade, you draw, you match the picture with the, it's not second grade, but picture with the command, okay? So it'll be like match the picture with the description, and except the description will be SVM, cost equals 1, gamma equals 5, and then another one will be SVM, cost equals 100 gamma 0.1 or something, right? And you'll match the picture with the output. Picture with the command. Okay, does that kind of make sense? So there's no calculations there, but you had an example in the homework where you kind of saw this, and I would encourage you to just try making up your own little data set and try running a few of these different things until you feel comfortable about the effect of what gamma does and the effect of what cost does. Okay. We've got k-means clustering. Here I'll provide a small matrix of data in 2D, maybe about 6 to 8 points. And I'm going to just provide some initial random, or not random, I'll say arbitrary initial assignments. And based on that, I'm going to ask you to perform like 2 iterations of k-means clustering. So, with the initial assignments, you'll calculate the centroids, redo the assignments, calculate the centroids, redo the assignments. And that will be that. I'll try to pick nice whole numbers so that when you calculate your centroids, it'll be fairly straightforward and easy. And I think I can do. We can do that. Maybe I'll provide a grid also to. I think that'll make it easier. Okay. And then kernelized k-means clustering will be done. So I'll provide an even smaller matrix of data in 2 dimensions. And again, some arbitrary initial assignments. And then a transformation function, a simple transformation function that'll go from 2D to 3D. We've seen a bunch of these examples already. And then I will ask you to do just 1 iteration of kernelized k-means clustering. Because once you're in 3D, you have to calculate the centroid in 3D, which is just a tiny bit more tedious. So just do 1 iteration, yeah.
So for this one, we're going to do like the manual method?
Yeah. Well, you'll transform it and do it. Because using the kernelized matrix is a pain to do it by hand, okay? So we'll just see, we'll do that. Okay. Yeah, so no using the kernelized thing. Okay. I've got the EM algorithm. I was trying to think how to do this. And what it's going to be is it's going to be the EM algorithm as a mixture of univariate Gaussian data, okay? So basically, I'll give you maybe 6 to 8 points, okay? Except these points are just one value, all right? It's not a coordinate in 2 dimensions. It's like 6 and 6.2 and 8 and 8.3, okay? Something like that, right? And if I were to give you the points like 6, 6.2, and 8 and 8.3, and I say, cluster these using the EM algorithm, you'd probably say, okay, we got maybe 1 Gaussian centered around 6 point something and another Gaussian centered at 8 point something. And that's basically kind of the idea here, right? I'll just provide some, what I'll do is I'll provide initial values for, it's going to be a mixture of 2 distributions, right? So I might say, your initial value is 1 Gaussian is centered at 7 and another Gaussian is centered at 8 or something like that, with standard deviation 1 or whatever. And then you'll use the Bayes classifier to find the probabilistic assignments of points to each component. And once you do that, then I will ask you to update the, let me close this door here. So you'll find the probabilistic assignments of points to each component. And it's you can do a couple shortcuts there, right? Because if the whole univariate Gaussian, you've got like the square root 2 pi business, but if we just use the same sigma for everything, so I'll probably be nice, and when I provide the initial values for the standard deviation, I'll just make it the same for both, and then you can kind of, that will be a constant that will cancel out. I mean, you can include it if you want to just be sure and careful, and stuff like that. And then, and anyway, once you get your probabilistic assignments, then I'll ask you to update the estimates of the means, and I'll just ask you for the update for the estimates of the means, because trying to update the estimates for the standard deviation is a bit more tedious. So the means, I think, is fair enough. Okay, does that kind of make sense for the EM algorithm? It's going to be just univariate Gaussian, some points, mixture of two components, and you got to try to estimate, what's the mean of component 1 and what's the mean of component 2. Okay, and then the last one, as far as calculation stuff goes, will be principal components analysis. I'll provide a small matrix, maybe 4 to 5 points in 2 dimensions, and then you'll find the principal components, and that you've kind of done the work for that. Well, I don't know. Homework 6 hopefully gives you a sense of what needs to happen. You'll center the matrix, find the covariance matrix, and find the eigenvectors. And you might need to review your linear algebra notes for finding eigenvectors. And I think I put in 2 links here. One's from Khan Academy, and I'm sure you can search the internet also for how to find an eigenvector of a 2x2 matrix. But I think that is simple enough and reasonable enough to ask you to do. Especially if I give you, quote, nicer numbers for the values. Okay, and then you'll project the data onto the first eigenvector. Okay. And then I'll have some conceptual questions. And the conceptual questions might span the entire quarter, okay? So the other topics, as far as like having to do this work and calculations, this is all stuff after midterm 2. But the conceptual questions will, go back. Okay. Yeah, question.
For like K and then K means, so if you provide a grid, we don't need to show work for distance, we can just look
Yeah. I think so. I think that's okay. All right, any questions? Good? All right. Okay, well, I didn't know what to do, so we'll have a bonus lecture. Maybe decision trees, maybe. Okay, yes. Well, I mean, that's what I put together today, so that's what you're getting. Okay. So decision trees are like kind of the building blocks for a random forest, and I think we've heard of random forest, or maybe we've used random forest. And I don't know how it was presented. I don't know if it's presented as just kind of this mysterious black box where it's like you give it your data, you say, make me a random forest, and then it outputs stuff. So basically, the random forest is built out of decision trees. And I don't know if anybody covered how a decision tree works in the first place. So I thought maybe we'll talk about decision trees, and then we can talk about random forest after that. I don't know. Okay, so this is what I'm calling bonus content. It's not going to be on the final exam. I'm going to be teaching 101C this summer, and I'll present pretty much the same stuff here. So if you're also in my 101C class in this summer, sorry, you're gonna see this lecture again. Okay, but that's what we have. Okay, all right. So the way the decision tree works is it uses, basically you have your target variable. So decision trees, random forest, supervised learning. So we're going back to supervised learning where we have a value a target value that we want to predict. And we're going to try to predict it based on input values, okay? And the way we do this is we partition the data into smaller chunks, okay? And the way we partition it is we use one explanatory variable and it forms a binary split, okay? And this creates branches. So we don't have more complicated splits right now. I mean, research can be done in terms of like making more than a binary split, but the math gets messy, so we stick to the binary split, okay? So basically, if the explanatory variable is numeric, then we're gonna form a split here, okay? Where it's like you just pick some number, and the split will be if x is less than that number or x is greater than that number, okay? And then whichever side gets the equals, it doesn't really matter, but the kind of convention is x less than k versus x greater than or equal to k. Mathematically, it probably doesn't really matter. Well, if it doesn't matter if it's continuous, and it does matter if it's discrete, but whatever, okay? If the explanatory variable is categorical, then you have to kind of form splits, you know, in terms of like x is an element of A and B versus x is an element of C and D, or something like that, things like that. And we keep doing these binary partitions until a stopping criterion is reached. And after all these partitions have been made, then all the partitions that fall in a single terminal node or leaf of this tree that we've created will share a single predicted value, okay? And so decision trees and regression trees generally will only have like, well, not generally, will only have a discrete number of values that it can predict, okay? So if you have a tree that has, you know, however many branches and 8 terminal nodes, that tree is only able to predict 8 distinct values, okay? It's gonna say, if you follow under this category, we're gonna predict your number is 22. And if you follow this, you know, path on the tree, we're gonna predict your number is 17 or something like that. And it's only able to predict 8 distinct values versus something like linear regression, where depending on, you know, you can have infinitely many x input values and you can have infinitely many y output values, okay? Decision trees can only predict a set, you know, however many leaves you have, that's how many distinct values it can predict, okay? And we have 2 types of decision trees. You got regression trees, which predict a numeric response, classification trees, which predict a categorical response. So, and today's lecture, we'll just look at regression trees for numeric response. Okay. Oh, no view quizzes for week 10. So no view quizzes today, or Friday. I don't know what we'll do on Friday. Maybe I'll talk more about trees and forests, or we can just do some pizza party. No, I'm not. No pizza party. Okay. Okay. So we'll look at regression trees today, and this is used to predict a numeric response. And basically, we'll talk about how the regression tree chooses to create a partition. And what it does is it's going to consider all possible partitions. It looks at every possible partition, and it makes a greedy decision, okay? And it's going to choose the split that's going to minimize the residual sum of squares after making the split, or it maximizes the reduction in the residual sum of squares. And it's greedy in that it only looks one step ahead, and it wants the thing that minimizes the next thing just in that thing, right? So maybe the word we use is greedy, but perhaps it's maybe instant gratification is a better concept. It just looks one step ahead and says, what's the best thing to do one step ahead, right? And if you only if you are guided only by instant gratification, all of your life choices are easy, right? Because you just say do the thing that's going to feel the best right now. Now, that is not the best way to live. And you guys are in college, so you obviously know this, because being in college is not necessarily the best instant gratification choice, but the idea is, I don't want to say pain, but but the work that you're putting in now, we're expecting will pay off in the future. And so, decision trees, they can't think more than one step ahead. So there might be a better split if you do a suboptimal split now. There might be an even better split in the future. As far as regression trees and decision trees go, it doesn't do that. It just says what's the best right now, and that's what we do. Here's an example of a decision tree that was actually published in mainstream publications. So this actually showed up in the New York Times. This was way back in 2008, and this was at the start of I don't know how old you were in 2008. This was when Obama was running for president, and at the time, during the primaries, it was Obama versus Clinton in the primaries, and Obama eventually won. And there was kind of this was maybe early on in the primary season, and so some of the primaries had already completed, and they were trying to predict what's going to happen to the remaining states that are going to go through primaries, and is Obama or Clinton going to win? And they did a decision tree. And the decision tree is simple enough for, I think, a reader to read and understand. Once you start doing bagging and random forest, it gets more complicated, okay? But basically, each kind of question says, the first one says, is a county more than 20% black? And if the answer was yes, it says Obama wins these counties 383 to 70 out of the, and if the answer is no, then you have more kind of these questions to ask, and it says, it has all of these things. And it's interesting. This is like a little time capsule going back to 2008, and it's interesting to see which counties voted for Clinton, because if you look at these things, I think I don't think these counties would vote for Clinton anymore, type of, but things were quite different, I guess, 14 years ago, back when you were, 5? Okay. And, all right, so let's just do a simple toy example. And here my X values are 1, 2, 3, 4, 5, okay? And the values that we're going to try to predict are Y, which are 1, 1, 3, 7, and 8, okay? And so we form a baseline. A baseline is, what if there's no partition? This is kind of like the null model. So when you talk about RSS and your linear model, and you talk about your R squared value, it's a improvement compared to the null model. And the null model here is the same as the null model in linear regression, which is basically you predict the same value, the mean, for everybody. Okay, and so in the case of a decision tree, there's no partitions. We're predicting the same value, which is just the mean for everybody. And so we just say, okay, what's the mean of 1, 1, 3, 7, and 8? And you add that up and you get 20. 20 over 5 is 4. So our y hat is 4. That's the predicted value for everybody. And what is our RSS? So each residual, I guess I did absolute values here. So 1 minus 4 is 3, -3, but I guess pretend these are absolute values, okay? And then we square these, and we add all of these up, and the RSS for the null model is 44, okay? And this is going to form a baseline, and we're going to say, can we improve the RSS by including some kind of partition? And so the way decision trees work is we're going to consider every single possible partition. And so with 5 data points, 5 unique values of x, we can form 5 partitions. Okay? And that, I'm sorry, 4 partitions. A split between 1 and 2, split between 2 and 3, split between 3 and 4, and a split between 4 and 5. So I guess step 1 is to sort all of your x. Okay, so I sorted them 1, 2, 3, 4, 5, and if some of the values were duplicates, then we can't form a split in between, like 1 and 1 or something like that. Okay, so here we're going to consider all 4 possible splits, and we'll see what the resulting RSS is going to be. So here's a picture of no partition. We put 4. These are the residuals, and if we square these residuals, we get 44. Okay, so we're going to consider all possible partitions. So the first one, we split x. We form the partition between x is 1 and x is 2. Okay, so this first value goes into partition A. The other 4 go into partition B. And we ask, what is the RSS here? So if you are in partition A, your prediction, there's only one value is 1. And so you would predict all values less than, where x is less than 1.5 is going to have y hat equal to 1. And therefore, in our data, our residual is 0, and the residual here is going to be 0 squared. As far as the other values, 1, 3, 7, and 8 add up to 19. 19 divided by 4 is 4.75. And if we calculate the residuals, okay, we'll get 3.75, 1.75, 2.25, and 3.25. And we say, okay, what are the squares of these things? And when you add all of these up, you get 32.75. Is that okay? As far as how I got the predicted values and this. So again, with a decision tree with only one split, we're only able to predict 2 unique values, okay? And so this is what our picture looks like. Here I've got a split at 1.5 and a split, and so the value down here we predict exactly, and over here this is the value we're predicting, 4.75 for everybody. So we have big residuals over here and here, and that's the total. Okay, what about a split between 2 and 3? Okay, so if we split between 2 and 3, then the values in partition A, the predicted values are 1, and so we have no residuals there. And on the other hand, the other values are 3, 7, and 8, and so our predicted values there is going to be the average of 3, 7, and 8, which is, did I add this wrong? No, I added that. Okay, 18 over 3 is 6. Okay, and so we predict the mean of 3, 7, and 8, which is 6. We calculate the residuals, we square them and add them up, and we get a total RSS of 14. And so this is the prediction here. So no residuals here. We're predicting 6 for all of these values, and that's the resulting RSS. Okay. Let's try a split between 3 and 4. So we'll say if x is less than 3.5 or greater than 3.5. And so if you are have an x less than 3.5, we have 1, 1, and 3. And so the predicted value, if we add these up, is going to be 5/3 or 1.66. Meanwhile, if you are greater than 3.5, then our predicted value is going to be 7.5 because the 2 values over here are 7, and 8. So if we square all of these things, the residual here is 0.66. I guess I decided to include minus signs here. Sorry for the arbitrariness of whether I'm using absolute values or not. Okay, so anyway, 0.66 and 0.66 squared is 0.44. Over here I've got 1.33. 1.33 squared is 1.77. And then 0.5 squared is 0.25. 0.5 squared is 0.25. And so when you sum these up, the RSS for this split is 3.1667. Okay, this is our diagram here. So that looks pretty good. And then lastly, we keep going and we consider all of our splits, and we say, all right, what if I split between 4 and 5? Okay, what is the predicted value for the values in partition A? 1, 1, 3, 7 adds up to 12. 12 over 4 is 3, so we're going to predict 3 for all of these things. What is the predicted value for this? Well, it's just going to be 8. So we have no residual here, and we square these residuals, and we get 4, 4, and 16 for a total RSS of 24. And this is kind of the diagram that we get there. Okay, so looking at all of our potential splits, we would say, okay, well, this one's the best split. This one ended up with an RSS of 3.1667. Okay, so we go through our data, and we would say, this is where we would split. We would split between x equals 3 and x equals 4. That's the one that's going to reduce the RSS from 44, which is kind of our null model, no partition, predicting the mean for everybody. And if we create a split at between 3 and 4, it'll drop our RSS down to 3.1667, which is a pretty significant reduction in RSS. Okay, and that's just by having 2 unique values to predict. We're either going to predict 1.67 or 7.5. Okay, what if we wanted to run this in R? In R, there's a couple libraries that will do trees. There's library rpart, library tree, and I'm going to cover using rpart. Rpart being basically a partition making thing. And so we're going to say predict y based on x, y as explained by x. We give it the data, and there are basically options that you can do inside control. All right, and by default, it says rpart says it's only going to consider a split if you have at least 20 observations. And so it would not even work for this toy data set. But so I'm going to say, all right, just still consider a split even if you only have 5 observations, because we're doing a toy data set. So here's my data frame, 1, 2, 3, 4, 5 for x. Y is 1, 1, 3, 7, 8. And then I say predict y based on x using the data frame, and then consider a split at even if you only have 5. And so it goes through and it says, ta-da! And this is the result, all right? And this result mirrors exactly what we have, even though it's a little bit harder to read. So let me go through what the output here says, okay? Here it says there are 5 values in the root node, and the total RSS, the total square deviance, is 44, right? And we saw that, okay? That was the total RSS. And it says the value that we would predict at this node, if we had to predict one value for everybody, is 4.0. Here, it says you can do where you would do the split is at 3.5. X less than 3.5 versus x greater than or equal to 3.5, which is what we found as well, right? So we're going to split between 3 and 4, and so it says do the split at 3.5. At 3.5, there are 3 observations in that node. The predicted value is 1.667 for those 3 observations, right? So if we go back to this thing, the predicted value is 1.667. And if you add up just the squared residuals for these things, these squared residuals would add up to 2.667. And then if you do the split for the values greater than 3.5, there are 2 observations there. The predicted value there is 7.5. And the squared residuals add up to 0.5. So the total squared residuals would be 3.167 if you add these 2 things together, which is what we got back here, right? So we predict 7.5, total squared residuals of 0.5 for a total of 3.1667. So the same results right here, okay? And I think I've broke it down onto this slide as well, but that's the output that matches what we got in when we did it kind of ourselves. And so when you do rpart in R, it considers all the possible partitions, and we get the same results that match up. Okay, so that's good, right? Anytime you do something by hand and it matches what the computer does, it feels good. All right, you can run something called, you can do summary, and it gives you a little bit more information. Okay, and so here we get there's something here that says, that's called the complexity parameter. Complexity parameter, and it gives me a value of 0.928. 0.928. And basically that value, where do we get 90.928 or 92.8%? It says how much of the RSS was reduced at that split. So we went from 44 to 3.1667. That's a reduction of 40.83. Now 40.83 divided by 44 is 92.8. So that's where it's getting this number. So this complexity parameter is a measure of kind of the amount of improvement we get by including this split. So, we got improvement of 93% in this. So it's a very good, drastic improvement by just including this one split. You can create a plot of the tree. This is the most boring plot because it's just a binary split. But if you were to have something more complicated, back on this slide, it would produce something like this, not without the faces, but it would kind of present something a little bit kind of like that. And here basically it says the question is x less than 3.5, and if the answer is yes, you go down the left, and the predicted value is 1.667. And if the answer is no, you go down the right, and your predicted value is 7.5. Okay, so what do we do if we have a bigger data set, which is going to be the case almost always? Well, you just consider every possible split. And so let's say you have 100 observations and you have 5 variables. Then you have to consider potentially 495 possible partitions as the first split. So you look at every possible split between, for x1, you consider the split between 1 and 2, and 2 and 3, and 3 and 4, all the way up to 98 and 99, and the split between 99 and 100. So that's 99 potential splits, less if you have some duplicate x values or tied values in x. And so you have 99 potential splits to consider for variable x1. And then you go to variable x2, and you consider all 99 potential splits. Then you go to variable x3, and you consider all 99 potential splits. And you do this again and again and again. And so just for the very first split, you consider 495 possible splits. And that's just with 100 observations and 5 variables. And so I don't know if you've tried running a random forest or even just making a single decision tree. If you have a very big data set, this is a very slow process, okay? You have to kind of sort all of your x values for each variable and then consider every single possible split. And if you have like 20 variables and 1,000 observations, that's close to 20,000 possible splits, 19,980 potential splits. Thankfully, again, it's immediate gratification. It's a greedy algorithm, so you only have to consider that one split, and you don't have to do kind of this, what if I split here and what if I split here next? Because that would just square the number of possible decisions to make. So anyway, you would do that. The one that reduces the RSS the most is the one you're going to pick. And then once you make a split, now you have 2 nodes, and you repeat the process. It's recursive. Okay, we call this the R and R part is actually recursive partitioning, because now let's say we started off with 100 observations. We do a split, and it splits it into, say, 40 and 60. Okay. Now that we have 60 observations over here, we're going to consider all possible splits. So now you have basically 59 possible splits across 5 variables. And then you go, and then you do that, and you keep going until you reach some kind of terminal condition. You do go to the other side. You have 40 observations. You consider 39 times 5 variables, however many, 195 potential splits. And whatever you do, you just kind of recursively continue doing, looking for potential splits that will reduce your RSS. And you do this until you reach some kind of stopping criterion. The stopping criterion is often how many observations you have in a bucket. So you might say, we need to have at least 10 observations in a bucket, or 5 observations in a bucket, or something. Or you could say, don't go after you reach, a depth of 4 or 5 or 6. Okay, you say, the maximum tree depth is 6 splits. Okay, otherwise, if you if you allow your tree to overfit, basically you'll end up with 1 observation in each possible partition. And you could predict everybody perfectly for that particular data, but then it's not going to work well in real data, right? Like, I think we would consider it silly, but let's say we wanted to predict people's grades in this class or something, right? And you can look at a bunch of different variables, and it might be like, okay, let's look at someone's homework score, and if their homework score is above this or below this, then we'll create a split. Let's look at their midterm 1 score or something, and let's look at this and that, and maybe their grade in some other class. Maybe, I don't know what data we have access to, okay? And we want to do that. Now, if your partitions start saying like, okay, does this person's first name start with an A, B, or C versus it doesn't, I think we start recognizing like, okay, this kind of split doesn't make sense, and it's probably not going to generalize super well. And that's where being knowledgeable about your data set is important, because you're familiar with grades and how things work, you'd recognize, okay, the letter in the person's first name should not matter, even if your current training data, it looks like it does, because just by coincidence, everybody with an A, B, or C in their first names that start with A, B, and C happen to score really well. And so it might be a good predictor in your particular data set, but we know it shouldn't generalize to the population. And so if you're working with something completely unfamiliar to you, you might not have that insight, right? So I'm a strong proponent and strong believer in that you should have some basic familiarity with the data and be able to say, you know what, relationships between these 2 variables don't make sense. So anyway, that's what we do for a larger data set. Okay, once you do make a tree, we also, going with the tree analogy, we can talk about pruning a tree. And so the strategy is often make a tree that overfits, has too many leaves, has too many branches, has too many splits, and then you go back and you trim off, cut off the branches, or prune the trees that are unnecessary. Okay, so we're going to go back to the toy data set, and I'm going to let it overfit. And basically, we end up with 4 terminal nodes, and that's because we have 4 unique values in our Y. Our unique values were 1, 1, 3, 7, 8. So we have 4 unique values, and so the overfit tree looks like this. We predict 1 for values of 1.2. We predict this value for this. We predict this value and this value. So this has overfit, and you can see if x is less than 2.5, we predict 1. If x is less than 3.5 but greater than 2.5, we predict 3. If x is greater than 3.5 but less than 4, we predict 7. And if x is greater than 4.5, greater than 3.5 and greater than 4.5, we're going to predict 8. All right, and that's how we end up getting this overfit tree. 4 terminal nodes, number of unique y values that we have. So because it overfits, we're going to prune, And the pruning is the idea of we remove the weakest link, the weakest split, until a certain complexity is derived, okay? So which split should we remove first? Should we remove the split at 2.5 or remove the split at 4.5? Do we remove this split or this split? Okay, well, if we take a look at this, all right, this is what it says, and we're going to look at how much the deviance gets reduced, right? So we start off at 44. The first split reduced it to deviance of 3.167, 2.66 plus 0.5. If we do a split here, the deviance will result in 0, a total of 0 after the split. If we remove this split here, I mean, if the split at 4.5 reduces the deviance from 0.5 to 0. And we're going to ask, well, which one has the smaller reduction in deviance? That's the less important split. So looking at this, to go from 0.5 down to 0 is a smaller drop than going from 2.6 to 0. So that's basically what this slide says. It says we would go from 0.5 down to 0 versus 2.6 down to 0. And that shows up in our complexity parameter. 2.6 out of the total of 44 is around 6%. 0.5 out of a total of 44 is around 1%. Okay, and so we're going to see these numbers 0.0606 and 0.0114, indicating basically how much of the error is reduced. So the first split reduces the RSS by 0.928. The next split, if we're ranking the splits, the next one reduces it by 0.06, and the next split reduces it by 0.0113. And then here we have, and there's a baseline coming from my command, which says just consider reductions of at least 1%. And so this just ends up doing it, right? And so here it says which node and which split do we have, okay? So node number 2 corresponds to a reduction complexity parameter of 0.0606. If we have this is what we end up getting. So versus at node number 3, this complexity parameter is 0.011, and so this is the one that's the weakest and we would remove. Okay, so we can say, so we just have to pick any number that's bigger than this value of 0.011. So if I say, so we're going to prune the tree. So we take this tree, the TR1 is the tree that's overfit. We're going to say prune tree1, picking a complexity parameter of 0.02. So it's going to remove any kind of splits that have complexity parameters lower than 2%. So we can see it removed that bottom thing, okay? And we can kind of keep improving, and we can say, okay, what if I want to prune it again with a complexity parameter of 1%, or 10%? So it would remove this one, which had a complexity parameter of 6%, and that's how we do it. Okay, we're out of time. You can look at these notes. This was bonus content anyway, so no biggie. But there's a few kind of tools that our part comes with that allows you to kind of decide on a complexity parameter. Okay, we'll see you guys on Friday, and happy week 10. Hang in there.